Okay. I have a deal to propose to you. Okay? As you may have heard or realized, we're running slightly behind schedule. So Nati, and this talk is actually scheduled for 60 minutes. Now Nati tells me that lunch is going to start at 1:30. And being in Israel, that means that lunch is, of course, not going to start until 1:40. So what I'm going to do is I'm going to combine this, I'm going to compress this talk to 40 minutes. Okay? And then we all head for lunch. Does that work for everyone? Perfect. Okay. So this is the hands-on intro to Trove. And Trove, as you may or may not have heard, is the latest addition to the integrated OpenStack codebase. Trove was added with the OpenStack Icehouse release. I mean, it was added earlier, but it saw its first official release with the Icehouse release. And it is a service that provides database as a service on the OpenStack platform. I'm going to start with a very brief introduction of database as a service. When we talk about database as a service, what it really is sort of a step up the stack from a pure infrastructure as a service platform, which OpenStack originally is, toward a platform as a service project. So infrastructure as a service, or IaaS, is primarily concerned with providing infrastructure, that is servers and networks and storage volumes and the like. And that, of course, opens the possibility that, well, maybe that level of abstraction is not quite sufficient. And wouldn't it be nicer if we could instead provide our users with platforms on which they can then build applications? Now, when we talk about applications, pretty much any application that you could think of needs some sort of a data store. And very simplistically, that could be an object store or a file system. But very frequently, that's actually a database. A database of some sort, possibly a relational database like MySQL or Cassandra, but potentially also a relational database like MySQL or Postgres, but potentially also a NoSQL data store like Cassandra or Riak or Redis, etc. So some sort of data store. So everyone needs one, but does everyone need to build their own? Because, as I'm sure you, by the way, who in here has a DBA background? A few, right? So I'm sure you'll agree with me that every database system that you've worked on has some better or worse support on specific platforms, has its own little arcane idiosyncrasies when it comes to requirements for hardware and system tuning, and some of them also have interesting flavors and forks and branches. Of course, the MySQL database is kind of a prime example for this. And navigating that mess can be rather difficult. And it becomes increasingly worse when you, as the DBA, who should really be focusing your expertise on database optimization and not some sort of operations magic, when you no longer have full control over the system platform. And that is exactly what is absolutely common in cloud configurations. So in a cloud, you have little or no control over the actual infrastructure. In the iron and wires type traditional data center, as a sysop or as a DBA, you wield a certain amount of clout over your system's infrastructure. You can ask your hardware team for specific hardware, for specific controllers, NICs, and the like. And in a cloud, that's absolutely not the case. Everything's virtualized. That includes your machines, your networks, your storage, everything. And everything is also expected to be elastic and scalable, and we have access to management APIs, and we can use orchestration facilities. So that's on the plus side. On the minus side is you have very little control over your hardware. And we also have, in cloud environments, we typically have relatively limited quality of service capabilities. And that is particularly true for OpenStack, whose QoS support currently is rather rudimentary. And guaranteeing things like I/O or network bandwidth is relatively difficult, albeit not impossible. It's just difficult. So how can we solve this? Well, one approach to this is that just like the DBA previously had to know a lot about hardware and systems, now they need to know everything about the cloud. But that's kind of suboptimal, because what we're doing is we're turning a DBA into a cloud operator, and what we really want is to get the most out of our database for our applications, and that's what we want our DBA to work on. So there's an alternative, and the alternative is to provide the database as a service in your cloud environment. So something that we can create and manage and interact with through cloud APIs using the very same command line interfaces and GUI tools that we use to interact with the rest of the cloud. So in other words, now that we no longer care about how our cloud creates VMs or volumes or networks or storage images, storage volumes, we also no longer want to care about how internally the cloud creates a database. We basically want to be able to tell our cloud, give me a database, then go on our coffee break, and when we come back, we want a working database that we can interact with and that we can build applications on. As with many other things in OpenStack, there is sort of a precedent or an inspiration in another established cloud platform, namely Amazon Web Services, and that is Amazon RDS. That is the reliable database service, which is DBaaS that has been available in Amazon Web Services for some years. So that's fairly typical about OpenStack, that it takes some inspiration from something that's already present in AWS. But as is also typical for OpenStack, with our own DBaaS, we aim a little higher than what's in RDS, because RDS is fundamentally limited to MySQL. OpenStack DBaaS does not want to limit itself to just MySQL, and it also doesn't want to limit itself to just relational database management. So what Trove does, in fact, is it manages MySQL and other relational database management systems just like it manages MongoDB or Cassandra. So here's a quick intro to OpenStack Trove. The motivation behind Trove was to provide database as a service within the OpenStack framework. Now, what does that entail? Well, it means that, like any other OpenStack service, it must support RESTful HTTP and HTTPS APIs that pass around JSON and XML objects. It must follow the established OpenStack API conventions. It must support authentication, authorization, and access control through the OpenStack Identity Service, aka Keystone. It must plug into the OpenStack dashboard and the OpenStack CLIs. It must provide an abstraction layer for multiple specific backends, where those backends are implemented as plugins behind a generic API layer. And of course, it must use and follow the OpenStack development model, which means gated commits and peer review and lots of unit testing and integration testing and so forth. So those are all the expectations that you would have of any OpenStack project, and that is also true for Trove. Trove was originally named Red Dwarf. It is a project that originally got kicked off at HP, and the first public presentation of Trove was by Brian Aker at the Percona Live MySQL conference. Then it was still named Red Dwarf. It got renamed Trove last year. The original project name is the reason why there's some development scripts and things like that that are still prefixed with RD, which stood for Red Dwarf, as opposed to Trove or something. Trove was an incubated project in OpenStack. It had a relatively long incubation cycle, and it ultimately graduated with the in a graduation meeting that was right before the Havana cycle, the Havana Summit. And during the Icehouse cycle, it became an integrated project, and as a consequence, OpenStack Icehouse, which just dropped in April, was the first OpenStack release to include Trove. The original project sponsor of Trove, as I already mentioned, was Hewlett-Packard. HP, even though they started the then named Red Dwarf project back in 2011, they have for some time actually not been the most actively contributing company in Trove. That distinction is currently held by eBay and Rackspace. So those are currently the companies that provide the most commits and provide the most developer resources to Trove. Another interesting aspect, by the way, for those of you who are OpenStack contributors, is Trove has a relatively high number of what we call drive-by contributors. That is to say, people who have contributed 3 patches or less. If we take the total number of Trove developers, over 2/3 are drive-by developers, which means that it's actually really easy to contribute to Trove, and the barrier to entry and the threshold is very low, which points to the project being well organized, reasonably well documented, and reasonably accessible for developers. The current PTL, the program technical lead in Trove, is Michael Basnight from Rackspace. Now, shifting gears a little bit and going away from sort of the motivation and the project history and actually talking about what are the moving parts that we have in Trove. Please recall that it's a general rule in OpenStack or for OpenStack services that OpenStack abhors a monolith. We don't like to have monolithic services in OpenStack. And so just as with everything else in OpenStack, Trove is not one monolithic blob of code. Instead, it comprises several pieces, and it, of course, also builds heavily on existing OpenStack components, because why on earth should it reinvent the wheel? So what are the building blocks that Trove builds upon within OpenStack? Well, of course, it uses Keystone for authenticating users, setting permissions and policies, and of course for maintaining the service catalog. So a Trove API service gets registered into the service catalog like any other OpenStack API service. Of course, Trove makes heavy use of Nova for acquiring and using compute resources. It makes use of Cinder for providing databases with persistent storage, and it supports either Neutron or Nova Network for network and IP address management. Trove itself consists of a number of services. The one that users will be interacting with most directly is Trove API. So the Trove API is a standard OpenStack-style RESTful HTTP, HTTPS service that clients directly interact with. Behind the scenes, the API passes calls to the Trove Task Manager, and the Trove Task Manager is then responsible for actually firing up the correct guest type based on a typically specifically configured image, creating and assigning persistent storage, ensuring IP connectivity, everything else that you would expect from a new VM being fired up. And then the interesting part is within the image, we have the Trove guest agent, and the Trove guest agent is what configures a data store and then enables the user to create databases and users and modify the database configuration through the OpenStack API. So none of these things do you still need to do from directly within the database, like creating a user or assigning it permissions or granting it access to a specific database. You can do all that through OpenStack API calls. There's a few other services that Trove also consists of, among them the Trove Conductor, which marshals database backend database access like Nova Conductor and Nova does. There's Trove Scheduler, which manages recurring tasks. But those are sort of lesser importance. These three are the ones that are really important. The Trove API that you interact with, the Trove Task Manager that actually translates Trove API calls into setup tasks, and then the Trove Guest Agent, which actually enables you to interact with the data store directly. Let me define a little bit of Trove terminology. I'm going to walk you through these 5 terms here really quickly because they're going to be important for the rest of the discussion. A data store is sort of the umbrella term for all the technologies that Trove can manage. So there's individual backends that Trove can support, and that, by the way, contributors can add in a pluggable fashion. MySQL was the first available data store, but others have been added and others are expected to be added in the future. So there's currently support for Cassandra and Mongo and Redis. There is support for several flavors of MySQL, including Percona XDB. There's currently no support for Postgres. If you understand Postgres and you understand OpenStack, that's an excellent low-hanging fruit for you to contribute. Add Postgres support to Trove. But that is the general term, a data store. Now, a data store is linked to a data store version. So if our data store, for example, is MySQL, our data store version may be MySQL 5.5. And a data store version is effectively obviously linked to a data store type. It defines a specific base image, and it also defines a set of packages that are to be installed in that image. So what this enables us to do is it allows us to run, say, for example, multiple MySQL versions on our cloud in parallel. Because if you wanted to deploy DBAS, MySQL as DBAS in your OpenStack cloud, of course it makes sense to be able to offer your users MySQL 5.5 and then MySQL 5.6 and then MySQL 5.7 in parallel if that's what you want to do. Then we have an instance. For those of you who are MySQL or recovering MySQL DBAs, This terminology will sound very familiar. An instance is actually one instance of the server. So an instance would be, for example, a single MySQL server process running within a guest agent, running within a Nova guest. Instances are created by a cloud DBA. That is to say, someone who has access to only the cloud API, not the cloud backend. So there's no fiddling with sort of backend infrastructure. There are exposed API calls for creating an instance, and also the next level, which I'm going to get to in a moment, is then a database. So for example, this represents a single MySQL server installation if we stick to our example of MySQL.
What happens in a cluster?
Yeah, question was what happens in a cluster. As for OpenStack Icehouse, nothing, because clustering and replication is the big feature that is being added for Juno. So there's currently no clustering and replication support. Not even the API, the appropriate API changes landed before Icehouse. That is what they had planned. They basically wanted to get the API framework, the scaffolding in place for Icehouse. That didn't quite work out. So we expect to see all of that in Juno.
So, for example, Sandra
And
doesn't really make sense.
right, and what you're saying is correct in that some of this terminology doesn't make a whole lot of sense for other databases. So for example, the relationship between a database and a user, I'm going to get to databases and users in a moment, but the relation in database and a user is backwards between MySQL and MongoDB, right? So those are a few challenges that the Trove folks are about to solve here. Before I get to users and databases, let me show you my favorite feature. I think this is really cool. It's called configuration groups. With configuration groups, it becomes possible to quickly and easily design a set of configuration options that are known to work well for a specific use case of your database. And then you can deploy this configuration group to potentially hundreds of databases. And it gets applied pretty much instantaneously. So that's really, really cool because, say, for example, you find out this new, say, InnoDB tuning parameter for your MySQL, and you realize that this works really, really well with WordPress. And on your OpenStack cloud, you're hosting 10,000 WordPress instances. That's basically one change that you make to a configuration group, because you can apply configuration groups to instances, and then as long as they're applied, they auto-update as you change them. So that's really kind of cool. It's sort of a massive system automation and deployment and configuration management headache that this takes away, which is really cool. So instances, configuration groups, and then we have databases. As would be a relatively common concept to any MySQL DBA, a single instance can hold multiple databases. And then, of course, the interesting part here in Trove is that the DBA, again, doesn't need to fiddle with the instance directly to create databases, but instead we can use the OpenStack API to create and manage and destroy databases inside an instance. And by the way, it's the Trove guest agent that takes these administrative requests, which it receives from the Trove API via the Trove Task Manager, and then translates that into functionality that is Datastore specific. And what that also means is that there is at least conceptually no difference to the DBA between managing a MySQL and a MongoDB database or a database in any other data store that Trove supports. So you basically say, give me a database. I don't care how you do it. And if you combine that with the idea of configuration groups and basically a set of defined and machine-readable best practices, something really cool is sort of happening here. So the question was, where is state kept? So what you're talking about are things like, is this database operational? Does it require a restart? Has it seen any changes recently? Is that?
Multiple operations have to happen in order for a transaction to take place. For example,
Okay, hang on a second. You're talking about actually using and interacting with the database, and all of that state is in the database where it's supposed to be. And the database itself is stored on a persistent volume that is attached via Cinda to the guest agent. Okay, how do we get Trove operational? Well, of course, we need to install the required OpenStack services. We need Keystone, Glance, Nova, Cinder, and Neutron or Nova Network. We need to install the Trove services, obviously. We must create an image that includes the Trove guest agent and upload that into Glance. We must create a data store, and we must create a data store version. So those are a few steps, and of course, you want to automate those. So how do we do that? Well, the deployment story for Trove is, as can be expected, like right after its first official release dropped, one of relatively low maturity. So the only way to currently get Trove running without doing a fair amount of development work is RedStack, which is effectively Trove's wrapper around DevStack, which also takes care of creating and populating a data store. Ubuntu, by the way, is packaging Trove, including the guest agent, in the 14.04 Trusty Tar release. However, they have presently, at least at the time, at least as of right now, they haven't backported those packages into the Ubuntu Cloud Archive for 12.04. And if I understand their support policy correctly, then they're actually only supporting Trove in Ubuntu Cloud Archive for 14.04, which is the new LTS forward. In RDO, the situation is even a little worse, with only the Python Trove client package currently being available even in the OpenStack trunk repository. So we're hoping to see some better packaging there in RDO. Regardless, interestingly, developers at eBay have come forward saying that they are deploying Trove with Puppet, but have been sort of unable to disclose the code publicly, which they, however, want to do. They just haven't gotten around to doing it yet. So it's generally expected that those modules will eventually go to StackForge and become a part of the rest of the OpenStack Puppet modules. OK. We've installed Trove. What's next? And here is where I'm going to try and cut over to my demo, for which purpose I probably need to move this. So, oops. Nope, nope, nope. Let's do it this way. And pull this guy over here. There we go. And yeah, so sorry this wraps around, but I hope we can still manage with this. So this is an actual live Trove instance that runs on DevStack in Vagrant. If you would like to duplicate this, all of this stuff is on GitHub. If you go, well, basically, you could search GitHub for OpenStack Israel 2014-Trove. And once you found that, it's essentially a git clone and then a Vagrant up. And then about 2 hours later, you get a full Trove install. The reason why it's that is that it's ridiculously network intensive. It basically hits the network all over the place. So it just takes some time. But there's nothing else that you need to do. It's git clone, Vagrant up, and you're good. And then you get this. And then there's a little script in here. That's my little trove create.sh. And once you hit that, then it will actually create a Trove instance for you. OK, so the first thing that we're going to do is we're going to take a quick look at what are the data stores that we have configured here. Very simple. So that's just MySQL. And then we can do a version list of this guy here. And we also have just a single data store version installed here. Out of this, we created, oh, and by the way, I can also do a glance list. Whoops. Image list, of course. And there is that Ubuntu MySQL image at the very bottom. The Red Stack installer does create this for you. So it uses Disk Image Builder to build this image that runs MySQL and Ubuntu and the Trove guest agent. So what we have here now in our Trove list is we have a single instance. We call it test Trove. Of course, that single instance corresponds to a single Nova guest that is running. And what is that? Oh, I thought it was a question. And this is a Cinder volume that has been created with our Trove create command automatically and has been attached to this Nova guest. And this actually uses the appropriate instance. So if we go ahead and do a vagrant at 10.0.0.2, there we go. And that's now inside our test Trove instance. So as you can see here, the varlib MySQL lives off of our dev VDB, which is our Cinder image. And for some reason or another, Trove apparently defaults to using ext3 rather than XFS for MySQL. I don't know why, but that's the way it is. So, and by the way, all of this happened completely automatically. The only thing that I had to do is to do Trove create, and it created this Cinder volume for me. It attached it. It created a file system on it. It mounted it to the correct mount point, and all of that. And as you can see, what we also have here is we have a Trove guest agent that is running here and a MySQL daemon at the bottom. So Trove guest agent, MySQL daemon right here. And if we want to do a varlib MySQL, oops, I should sudo that. So as you can see, there is MySQL performance data, performance schema, and test database in there. So what I want to do now is I want to do a database. Nope. Here we go. I want to create another database, and I'm going to name that test2. What happened here is I used an OpenStack API call, the Trove database create. It hit the Trove API service. It got passed on to the Trove task manager, which then communicated with the Trove guest agent inside the guest. And now if we take a look here, then all of a sudden there's a test2 database here. Okay, so no interaction with the database here directly. I didn't have to log in as root and do a create database or any of that. I could just go ahead and create that. Now, the next thing that I want to do is I want to be able to actually interact with this database. Well, what do I need for that? I need a user, right? In my test run, I named this guy foo and bar. So now we're going to call the user bar and use the password baz. And we're going to let this guy talk to our database name test2. Whoops. Nope. That was premature. I, of course, need to do this first. So here we go. Bar baz. OK? So the syntax is Trove user create, and then I give an instance ID. I give a username, a password, and then optionally I can restrict access to specific databases. So in this case, I want to restrict it to the test2 database. So now I've interacted with the Trove API, the Trove task manager, and the Trove guest agent to create a user inside my database. And now, if I use this new user that I've just created, and I want to connect to, say, the test database, then it's going to say, not going to happen because you don't have access to that. And if I actually want to go to test2, then boom, lo and behold, I'm actually talking to a working MySQL database. In case you're wondering, for those of you who are MySQL DBAs, the user that's being created here is granted all privileges on database name .star with grant option. So in theory, you could now use this user to define additional users in the database. but really and truly, that's kind of a bad idea. What you should be doing instead is just use the OpenStack Trove API and the appropriate calls, such as Trove user create. And there's also a Trove user grant access call and things like that. So you can, of course, also modify existing privileges after the user has been created. OK, and now I want to show you, as I said, my favorite feature of them all, which are Trove configuration groups. So I'm here, and now I can do a show variables like, let's get our, so for example, look at the sync bin log here, right? So it's a standard out-of-the-box MySQL installation. Sync bin log is set to 0, and that's it. OK, so what we're going to do, again, from our OpenStack API is we're first going to create a Trove configuration group. So configuration create. It's a missing F. There we go. So that's the syntax here. We can create a configuration group. We can give it a name. And then it gets a JSON dictionary of values to be set. So for example, I'm going to do a Trove configuration create. I'm going to call it sync bin log because I'm not very creative. And then it's going to be sync bin log 1. There we go, and I just need to get my quotes correct here. Trove configuration create sync bin log sync bin log 1. That syntax should be right. Oops. There we go. Yeah. What was that? No, I did close it. There is a double quote at the end. See that? There we go. Sync bin log. Let's see if this works. Much nicer. So we've just created a configuration group, and the only thing that it does, it sets the sync bin log value to 1. So now what we can do is we can attach that configuration to an existing instance. So my configuration group is this one. And so we want to do a configuration attach. Now attach this config group. And what we've done now is we have now applied a configuration change to, well, in this case, a single database instance. But it could be 100 or 10,000 database instances that we applied it to simultaneously. And now if we do this again, there's our test 2. And lo and behold, our sync bin log has switched to 1. So the question was, does it restart the database? There are certain configuration settings in MySQL that you can set on the fly that do not require a restart, and some that do. The configuration or the data store provider knows about which which configuration group settings require a restart. When that happens, it sets a flag for the instance that states restart required. And you can do a Trove show. Let me do that real quick. There's a Trove show. And in this case, the status says active. And if you make any configuration change that requires a restart, then the status here says restart required.
Does it also add to the my.cnf file so that on restart we don't lose this configuration?
So the question was, does it add to my.cnf? Yes, it does. Yes, it does persist these settings. And that's also the reason why when you detach a configuration group, so you're not updating a config group, but you're actually detaching an existing one, that means that the status automatically goes to restart required, because what it does internally, it is just ditches those my.cnf or mysql conf.d files. And then MySQL does not automatically roll back those values to their defaults. So.
I mean, why would we want to let it automatically restart things without asking for confirmation, sometimes restarting?
The question was, why would we want it to automatically restart things? It doesn't restart automatically. That's the very point. So yes, you're completely right. We would like to restart the stuff manually. And that's why it's got this restart required flag. Now, of course, what you can do is you can basically look through your entire Trove instances and then basically say, all right, now restart everything that's marked restart required. If you're asking about whether that can currently be automated, to the best of my knowledge, only by your own scripting, but possibly that might change in the relatively near future. OK? All right. And again, as I said, all of this stuff that you just saw in this very brief, I wouldn't even call it a demo. I mean, it's trying out what Trove does for you. You can do that. It's all on GitHub. Just search for OpenStack Israel 2014 Trove, and then it's a Git clone and a vagrant up. So, and now. There we go. Ha. All right. Oops. OK, so that's creating a configuration group. You basically say Trove configuration create. You give it a name, and then you set a JSON dictionary of values. And you can also give it a description. If you're curious about how to list configuration parameters supported by a specific data store provider, there's a feature for that. You can attach a configuration group to an existing instance. You can detach it from an existing instance. And very importantly, you can also modify a configuration group on the fly. And that means you immediately affect all of the instances that the config group is currently attached to. This is also known as patching a configuration group. That's why it's called Trove configuration patch. And that means you can quickly and easily update potentially dozens or hundreds of databases. You can also find instances for a specific configuration group, delete a configuration group, what you would generally expect. By way of a very quick summary, what I covered today, why database as a service. It's a step up the stack from infrastructure as a service slightly toward PaaS. Pretty much everyone needs a database, and control over the infrastructure has now shifted away from the DBA to someone else who's typically not the DBA that runs the cloud. Trove is, whoops. Oh, interesting. There's a slide that dropped here. So Trove itself is DBaaS within the OpenStack framework. It was originally named Red Dwarf, was integrated for Icehouse, and it's currently backed by HP, Rackspace, eBay, and also Tesoro, which is a startup company that's sort of the first that actually is building their business on top of Trove. It builds on OpenStack Nova, on Glance, on Neutron, and on Cinder, and of course also on Keystone for authentication. It contains an API service, a task manager, and a guest agent. It can manage data stores, instances, databases, users, and permissions. And we also went over the deployment considerations, as in not really production-grade deployment as of this point. I mean, the code base is fine, but deploying it is not something that we typically run very well at scale. But that said, it's absolutely technology that you should look into, because it's something that we're going to see in a much broader scale, I think, very, very soon. And then apparently my last slide is not coming up. It's basically just a summary for creating an instance, creating a database, assigning users and granting permissions, and using configuration groups. Besides this talk being recorded, there's also an O'Reilly webcast on OpenStack Trove that I did a couple of weeks ago, and that's up for recording as well. So feel free to peruse that. And again, github.com/fghaas/OpenStack Israel 2014-Trove, but just search GitHub for OpenStack Israel Trove, and you will find that. If you have any questions or run into any issues with that, please let me know. File an issue in GitHub, and I'll be happy to help you out with that. I am no longer keeping you from your lunch. Thank you very much for your attention. Enjoy your lunch, and see you this afternoon.